All right, welcome everybody. It's another noontime session. This is one of many, basically our all-day workshop condensed into 1 hour segments. And today is all about HVAC retrofits. And some of you may know, and I put it up on my LinkedIn when I shared the post from New York Passive House. This is one of my favorite sessions because we're really deeply involved with doing deep energy retrofits with HVAC systems across the country. I'm going to share a lot of the details of that, and specifically a model that was developed by the Northwest Energy Efficiency Alliance. And we have some exciting things going on with taking that model to other markets and getting involved with utilities. And in the case of New York Passive House and NYSERDA, we are about to launch a initiative to do 15 pilot projects with this model. So and share the details today and really talk about the advantages it has. Local Law 97 is also something I talk about, and this has a very big impact potentially on meeting some of those requirements. So this you'll find is a very interesting model, and so we'll go through it in detail today. So I did put up Local Law 97 just to start this off because it is for the New York Passive House and those aware of this. It's a pretty big deal because all those commercial buildings in New York are going to be held to a standard for reducing their energy and carbon. And for some of them, they're looking at that and they are looking at a pretty big nut and the potential to have fairly big fines. You can see the penalty is $268 per metric ton over the allotted limit. I actually had a conversation with kind of a third-party conversation about a developer who was looking at, did the math on it for a cluster of buildings that the developer owns in New York, and we're looking at a $2 million a year fine. So it has their attention. So this, as I will share, has a very big impact on energy and carbon in buildings in New York and can have a huge impact. So bottom line is taking what they call unitary or rooftop unit systems that typically use gas for heat and electric for cooling and ventilation all in one. So on the left here, a packaged rooftop unit off the roof at end of life, when those are all done and looking to be replaced. And rather than replacing that with a dedicated outdoor air system with very high efficiency heat recovery combined with heat pumps. And heat pumps are already, I'll talk about incentivizing those, and our electrification, decarbonization, they are pretty much the tool that people are using. And so combining that with very high efficiency heat recovery ventilation gives you a lot of very positive results. So this is the from the Northwest Energy Efficiency Alliance. This model was developed, probably 10 years ago now, but sat on the shelf for many years because they were missing the very high efficiency commercial HRVs and ERVs. There just was not anything. And anybody that's been practicing in the passive house world knows that up until Ventacity and then Swigon has also come into the market, there was no passive house certified commercial HRVs and ERVs. I spent 15 years with Zender, so I was very aware of that. And I had people telling me to get the people in Switzerland to bring their commercial units to the North American market. When that became available first with Ventacity, that basically was the missing piece for this model. And so this is at the Better Bricks website, and this is the basically the front end for the Northwest Energy Efficiency Alliance, which is about 120 utilities in Oregon, Washington, Idaho, and Montana. Those utilities pool all of their energy efficiency funding, and it goes through the Northwest Energy Efficiency Alliance. So they came up with this model, and at very high efficiency DOAS, they have requirements and specifications, and one of them is Passive House Institute certified, or a minimum of 82% sensible, and then also efficiency on the fans, PHI certified, or very high efficiency on the CFM per watt calculation. So this is in their specification, as well as specifications on minimum efficiency for heat pumps to complete the package. And so when you get done, I've highlighted a few of the really important ones: significant energy savings, and we've proven 50 to 80%. We've even had better than that. And in the average, I'll share some details on that, is quite a bit higher than 50%. And this is the HVAC energy use in these buildings. Maintenance costs, lifetime of the equipment is generally a little longer than conventional rooftop units. This one that's highlighted, significant reduction in heating cooling loads and equipment sizing, is a very important factor when you are looking at the incremental cost from just replacing rooftop units to doing this with heat pumps and very high efficiency heat recovery. So you're looking at a reduction in loads can translate, and I'll talk about that, in reduction in cost of doing the systems. The other things that happen, and this was all done for energy efficiency, the real critical thing here is that what we were also doing when we were doing this was improving comfort, quiet, and indoor air quality. And I want to talk about that. In the age of COVID, all of a sudden this model became doubly powerful, because not only were we saving a lot of energy, we were also improving ventilation, which anybody that's been paying attention is kind of the magic bullet for dealing with COVID and indoor air quality and health in buildings. And so you can provide optimized ventilation. I'll talk about some specifics, and really deliver in the age of COVID and getting schools, offices, retail back to work. So this was the first project we did. You see on the left is before, on the right is after. So red is gas heating, blue is cooling. This is in Portland, Oregon. It's a 12,000 square foot office building. So red is gas heat, blue is cooling, green is fans, and gray is plug loads and lights. And so basically you can see the EUI reductions. We went from the building at 57.4 after. Now this building had minimal other improvements to the envelope. They did replace the windows, which were really, really bad windows. And they replaced them with better windows. So they got a little bit better air sealing because they sealed around the windows when they installed them. And again, better performance from the windows. But my recollection, the blower door test on this building was over 6. I think it was close to 8 ACH 50. So after it was completed, not a tight building at all. And it's an old brick building with modest R values in the walls and roof as well. So really this is about HVAC. So the HVAC energy went from 50.7 down to 13. And one of the big takeaways we've had from multiple projects that we've done, when we're talking to utilities, one of the concerns they have is that you're going to fuel switch. You're going to take the gas off and replace it with, in other words, gas heat is going to be replaced with heat pump heat. And you're going to shift the load from gas off the building to more electricity and increase the load on the grid. And that has its own challenges. But what you'll see here is we took it from 19.8 kBTU per square foot on electricity and 37.6 gas to 19.7 electric and 0 gas. So we actually nominally, call it left electricity flat, did not shift. We just got rid of the gas. And this has been consistent with multiple projects where we had good data on this. And we also did a reduction in the peak demand for electricity demand, and the electric utilities like that as well. So this is a summation, and this is available. There's a white paper that has all this information in it from the Northwest Energy Efficiency Alliance. Anybody sends me an email, I can send you this, or else you could go to betterbricks.com and find this. There's a white paper that outlines 8 projects we did. So a law office, a pizza restaurant, government office, utility office, that's in Montana. Airport terminal, this is the Boeing Field Airport Terminal at King County Airport, which is where Boeing builds airplanes in Seattle. Government dormitories are in Montana, so a colder climate, an office in Seattle, and a restaurant in Portland, Oregon. So you can see the post conversion where we took those values from, pre-conversion. This would be the second column here is HVAC for code compliant. And this is where we ended up. To look at that in terms of percentages, you can see those are the percentage reductions in HVAC energy. This utility district office showing 39%. We actually have reevaluated that and got more data. We discovered this is in Montana, it's actually utilities' own office. And because it's a utilities office and they have very inexpensive electricity, they were using an electric boiler to do, in effect, snow melt on their building in the wintertime. So we discovered they were, in effect, wasting a lot of energy. And when we kind of corrected that, things have gotten, it's closer to 50% now, I believe, is the corrected number with more data and a change in the way they were doing things. But you can see the average is about 70% HVAC energy savings, very significant. From a cost perspective, this was also determined. This is all in cost of the conversion. So you can see it is a fairly big range. You've got sometimes restaurants are a little bit more. They've got small restaurant, so there's just kind of a fixed minimum that you can do. And but a lot of the offices you can see are anywhere from $15 to $20. This was $22 a square foot. The airport terminal building was $35 a square foot, mostly because it's in Seattle and they could, and the county was paying for it. It's unfortunate, but they, I think, paid more than they really needed to, but that was the project, and you'll see I've got some slides on it. The savings are huge. This is in New York, so this is Tarrytown, New York. This was the biggest project we've done to date. This is a 71,000 square foot office building. It's 4 floors with a parking garage underneath. It was done while it was occupied, which is a big thing. So the tenants were basically not, displaced. They went in and did the work overnight and after hours for all the internal work. You can see in the picture here, potentially, there's the heat pumps being put on while the rooftop equipment was still in place. All this rooftop equipment is now gone, and what you have is 4 3,000 CFM ERVs on these pads up here, and the heat pumps, banks of heat pumps on either side for the building. And it was 50% complete on April 1st, 2019, so a year and a half ago. And we saw savings just in the first 4 months. You can see the significant energy savings. What you'll see here on these 3 graphs, this is where we found the building at the start. This was modeled if we just replaced the existing equipment with code compliant equipment. And then this was modeled for the heat pumps and very high efficiency energy recovery ventilation systems. We exceeded the model significantly, believe it or not. So when you look at that, we actually did much better than what's shown there. And this is a graph of electricity consumption and utility bills. And what you'll see here, this is very small print, but what you'll see here is the first 10 months, it was only half the building completed. So from March, April of 2019 through spring this year. And then the last 2 months, they had the full building. The other half of the building was commissioned. And the savings, the energy savings are shown at $153,000. Again, with half the building done for 10 of the 12 months. We anticipate, you extrapolate that, we're going to be at about $200,000 a year. So very significant. Here's peak electricity demand before and after. So the blue is before and the green is after. So basically we flattened that out. And so peak demand, Con Ed, which did incentivize this, Con Ed threw in $128,000 toward this project on incentives. And they're happy with the fact that we flattened out their peak demand. And again, we really just got rid of the gas and have almost no increase in electricity with the building completed. I think it's actually going to be less. So to look back here, to give you an idea on this, the cost of doing this replacement of the rooftop equipment was put at $1.7 million. And the project, as it was done with ERVs and heat pumps, again, done while the building was occupied, was $2 million. So they had a $300,000 incremental cost, $128,000 incentive from Con Ed, and $200,000 a year in energy savings. So the payback on this is actually less than a year for that incremental cost of doing that. One big thing here is now it has a dedicated outdoor air system with highly filtered, passive house certified ERVs, have MERV 13 filters standard. I'm going to talk more about indoor air quality coming up. So this office building in Tarrytown basically is COVID compliant, ready to open, with a capacity to turn the ventilation up over what it's designed for. We've got extra capacity on the roof. There's a total of 12,000 CFM on the roof. And they're in a position to basically open with optimized ventilation that is specified in healthy buildings going back to work. This is the King County Airport I mentioned. So when we found it, it had 3 of these very large rooftop units on, and now it's got 3 of these, 3 1,000 CFM HRVs and 4 heat pump systems on the roof. This picture says it all. HVAC EUI reduction, 89%. So that one is off the charts. And it's kind of low-hanging fruit. These are very inefficient and poor efficiency units, very large fans, energy hogs, basically. I think these are being repurposed for public housing in Seattle or something now. So we were looking at doing these projects all over. This is a gym in Maine, and Planet Fitness you may be familiar with. They're a national chain, and we looked at doing this gym. Unfortunately, they decided, you know, gym owners are funny, and there was an incremental cost, and he decided not to do this. And of course, reopening with recirculating rooftop units, I'm going to talk about, he's not going to be a popular place for going to the gym, nor are any of them. And had he followed our design, he'd be saving 66% in energy consumption as we modeled it, and about $5,000 to $6,000 a month. These gyms run 24 hours a day. This is in Maine, Portland, Maine, and the energy savings, $50,000 to $60,000 a year, goes a long ways to closing the gap on the incremental cost. So that's just how it's shown with the reduction in energy. Very significant. And as planned, it was rooftop units. As we had proposed was air stage VRF heat pumps and Ventacity ERVs on the roof. Give you an idea on this whole model, and it's very important to understand that, you know, you have to look at these things in terms of whole systems. I talked about load capacity and so forth, reducing that with outside air reduction in energy. We looked at a project, this is a daycare project up in British Columbia, so it's north of Vancouver, and they were looking at conventional ERVs, and their design temperature is 5 degrees Fahrenheit, and their minimum delivered air temperature was 55 degrees by specification. And so looking at that, they were going to have to put in a gas line into the building and run 3 gas-fired duct heaters to maintain at 5 degrees design temperature to get the air coming in up to that minimum 55 degrees. There's also outdoor insulation packages and bypass and dampers. And using very high efficiency ventasity units, did the design work on it, and at 5 degrees Fahrenheit, we were going to deliver 61 degrees Fahrenheit and meet the requirement without any post heating. And so they could eliminate, and did eliminate, the gas line, 3 duct heaters, gas lines to the duct heaters, controls, all the outdoor package insulation and bypass, which is all included on the Ventasity system. So the actual first cost for this project was actually quite a bit less than using conventional ERVs. And that's something that's really something to look at very closely, is as a whole system, how does that all work on this package and this model. This is just to give you an idea of the impact that you can have with very high efficiency heat recovery ventilation. This is a project, a mixed use project in Michigan, and we looked at this. So the outside air is 2,772 CFM by code. The exhaust air requirement's only 400, but you run that at balanced. But the outside air heating load is 203,000 BTUs an hour, 93,000 for cooling. If you use this very high efficiency heat recovery for that outside air, in other words, you're capturing 85% of the energy for the outside air load. We reduced it all the way down to 31,000. So the cooling load actually became the dominant factor, but they were able to reduce the size of these systems for the heating and cooling equipment dramatically. In this case, I'm showing 18 tons of reduced heat pumps at $1,800 a ton. That's just the equipment cost. The installed cost typically is about $6,000 a ton. So we were looking at, 6,000 times 18 tons. That's how much we were looking at, over $100,000 in savings on that project for the heating and cooling equipment by using very high efficiency heat recovery for your outside air. Then we demonstrate this with this is our selection tool. This, you can take any model, put in your summer and winter conditions, and it'll get you this is your total outside air load unconditioned, and then the HRV heating, cooling, or excuse me, cooling and heating, and the ERV heating and cooling, or cooling and heating, cooling on top, heating on the bottom. And so you can see what the load reduction is here. It's very significant. And so this is your remaining load is just here. So the heating load goes from 33 to 3, basically, 90% of it. Some of you may have seen these next few slides, but I like to just put this up because people don't always get the perception of the impact that outside air has on total energy. Buildings use about 40% of energy. New York City and large cities where very dense with buildings, high density buildings, 70%, up to 70% is how much energy the buildings use. Outside air accounts for 30 to 40% of building energy. In a house, that's a bath fan blowing warm air out in the wintertime and pulling cold air in through the cracks. That's energy to reheat that air. And in large commercial buildings, that's bringing in outside air, having to heat it, cool it, potentially dehumidify that air. All that takes energy. And so the outside air component of the whole HVAC energy is 30 to 40%. In a passive house, so when you're talking about very high performance buildings, that percentage is going to be even higher because your heating and cooling loads are so significantly reduced by your exceptional envelope with air tightness and building air tightness and insulation values. Throw in some solar gains when it's optimized, and your HVAC energy, the total percentage that is shifted to ventilation is even higher. But looking at that, buildings use 40% of all the energy. Ventilation accounts for 30 to 40% of that energy. That means ventilation accounts for 12 to 16% of all the energy we use overall. So providing ventilation, not enough talk, not enough concentration, not enough consideration taken to the ventilation component in our mind in buildings. And now everything's changed because COVID and a pandemic have changed the ventilation conversation probably forever. All of a sudden, people are focusing on ventilation in a very big way. And so that outside air load becomes even more important. And I see oftentimes ASHRAE guidance and World Health Organization guidance, when I've seen papers and articles and guidance, position papers, they talk about that outside air being an added energy impact, and it's going to cost us all this energy. But I think if you really look at it in a bigger picture, potentially you could actually reduce energy in buildings dramatically while you're still at the same time improving the indoor air quality and health of those buildings. And that model that we've developed goes a long way to do that. And ventilation is really critical, and we are seeing, all these studies. What's funny is if you look at the dates on the right-hand side there, these different studies, 2013, that's a little more recent, California's classrooms, finding that absences decrease with increased ventilation rates. This is all about health, these 3 studies. But this has been going on since 2002, 2004. So we've known that classroom ventilation is not good and that it is having a negative impact on health in those classrooms. Spread of germs, spread of flu, colds, and so forth is really what you're talking about for absences. And then we're talking about here, ventilation and its impact on cognitive function, test scores, and learning ability on these other studies that were done. And so that is something, again, none of this is new, but all of a sudden it's top of mind. So ventilation is critical. And so if you can reduce energy dramatically while you're also improving the ventilation rates with balanced whole building ventilation, it has a big impact. So one of the things that we have as takeaway on these projects, they were highly monitored and measured and verified for not only energy efficiency, but in most of the projects, they were measuring comfort. So this is the temperatures and the different spaces in that first office building in Portland I showed you. So you can see it's very consistent that the conference room you'll see varies because people come and go in the conference room. So it had a little bit of a swing, couple degrees, but the rest very consistent as far as comfort goes. And then here's the health side. CO2 levels indicating air changes and consistent ventilation, effective ventilation. This is a 600 parts per million line, and we were pretty much hovering right around that or below. So consistently, every one of these projects, the big takeaway was the people that worked or lived in those buildings or spaces would tell us, this is great. They could feel it day one when we had the building commissioned. And they would comment to their bosses and so forth. It just feels healthy in here. Bill B commented here. I'll just see this in the chat. Ventilation units do not have DX coils and only rail, and the heat exchanger reduce latent load, and then the VRF system has to pick up the balance of the latent load. System, what happens to the space with relative humidity? Just an update, Ventacity has DX kits for all of our systems, and we are installing them all over the place now. And we are doing DX coil kits that can tie into an existing VRF system or do a dedicated outdoor unit for the heat pumps. We've got a 7-Eleven store in Boston with that system. We've got a school in Massachusetts with that system. We've got a lot of projects going that are going to leverage DX coils on the ventilation to do just that, do a little bit of extra latent load management on the ventilation system. So back to the indoor air quality here. This is, you know, the whole COVID thing, and I've talked specifically to this, but this is the Rudnick Milton study was in classrooms, and they were actually studying, this is done quite a time ago, and yeah, this is shown as 2003. They found in classrooms the ventilation, and they use CO2. So the bottom axis here, the horizontal, or the horizontal axis is CO2 levels from 400 up to 3,200. And then this is the probability of infection. So 10, 20, 30, 40%. This is a classroom with 30 students and 1 student infected. And then these lines, the orange line is 1 hour, the gray line is 4 hours, the yellow line is 8 hours in that classroom. And so what you've got is, if you keep the CO2 levels at 1,000 here, the red line, you can, it's pretty simple. The curve goes up dramatically the higher the CO2 level, which indicates the poorer ventilated classroom is going to have more spread of, in this case, they were looking at the flu, but it would be very much applicable to what we're dealing with today. So this is something that is common sense. Everybody pretty much gets this: better ventilation, better air changes, less chance for viruses to spread. And the critical thing is that that air in the classroom is being exhausted directly outside with no cross-flow contamination where it gets into the incoming air and not recirculated. So this is stuff that's out there. It's been all over the place. So no recirculated air is highlighted here, and MERV 13 filters highlighted here. So that's been 2 check marks, and doing passive house ventilation, the heat recovery hits on those things. Our RTU replacement program, to kind of demonstrate this, rooftop units work by recirculating air. So it heats it or cools it and then puts it back in, and it gets distributed into the space, and then there's a return, it comes back, it gets reheated or recooled, dehumidified, and put back in. And there's a damper that opens and lets a percentage of outside air in and circulates that. In effect, it pressurizes the space with outside air, typically. As opposed to a balanced ventilation system with direct exhaust that goes outside and then fresh air coming in, and the two shall never mix. And from a virus perspective, I sincerely believe that recirculating rooftop units are part of the problem. It's almost inconceivable to me that nobody's really studied this and put it in a lab and run a rooftop unit typically, or a unitary system that recirculates this way. Typical filters are 6 to 8 MERV, and I am perplexed that nobody has really studied it. It may be because there are millions of these on top of roofs across the country, and nobody wants to really know that these things are spreading viruses. But it does make sense that that's very viable possibility.
I just would like to chime in on one thing. ASHRAE did do a study, and they compared a DOAS unit to a recirculating VAV system. And the VAV system had the same amount of outside air as did the DOAS system, but the key was, and it did allow recirculation, the VAV system, but it had MERV 13 on the return. not the standard MERV 6 or MERV 7. And they claimed, and I can show you, send you the results, that the actual pathogen concentration dropped with the VAV system allowing recirculation with the MERV 13 as compared to just the DOAS. So, I mean, their position is you get rid of COVID by several means. One is displacement, outside air changes. The second one is filtration, where you use very efficient MERV filters. So that is not a detriment. That actually helps you. And the third, which we're investigating, is deactivating the pathogen altogether, like bipolar or UV or whatever.
Yeah, we're working with some of those people, GPS
right.
and others.
So, and answer your question, at least according to ASHRAE, they're saying that if you do recirculate, that's not detrimental, providing, and that's emphasis on the word providing, you have like the MERV 13. If you just have a lower MERV 6, it's not. You're probably gonna have a problem.
And one of the big challenges there is kind of like making chicken salad out of what. Most rooftop units, the fans are engineered and designed for a MERV 6, MERV 8 filter, and putting a MERV 13 filter in is going to cause all sorts of possibly limitations or extremely high energy use for the fans, or even burning out the fans. This I know from talking to HVAC contractors all over the country. And retrofitting existing equipment that's not designed or engineered to do that is a big challenge.
Well, yeah, the fan has got to have enough reserve capacity where you can
right.
change the shivs on it, or you can pump up the VFD, but there's a limit. You can't go forever. Yeah.
Right.
And you're certainly going to have more static, no doubt.
Right. And are the fans designed and engineered for that higher static, especially as a MERV 13 filter is going to clog more readily, and that static curve is going to be much sharper with a 13 than you would have with a 6 or an 8.
Right.
So yeah, I mean, there's a lot of issues with it. Bottom line is a balanced whole building ventilation system with no cross flow contamination is, especially if it's a system designed and engineered to use MERV 13 standard, is going to be an optimum way to do that.
Yeah, the catch is now the new MERV, the newer filters, they claim. If you look at the static pressure drops, I mean, certainly as you increase the MERV level, the static's going to go up, without a doubt. But they're saying that the new MERV 13s as compared to the old MERV 13s, the static increase is not as much as nowhere near as much as it used to be.
Yeah.
Because of the nature of the filter media that they're using and so forth.
Right. What we're looking at and having a lot of conversations with is existing equipment, trying to open these buildings, and the building owners are looking at, what do I do? From a new perspective, you go with ASHRAE, but really what I'm talking about is this model is pretty powerful, because you can take something like this that isn't designed to use a MERV 13 and so forth, and we really stress it's end of life. And we are doing this with a good number of office buildings right now where they want to get back and bring people back. And so they're doing this solution and replacing the rooftop units with dedicated outdoor air systems and heat pumps. And they're going to save a huge amount of energy, which means they're saving a huge amount of money, so they can afford to do this retrofit and improve the health of their building. So it's a pretty strong model.
It certainly depends on the nature of the specific heat pump that you pick. I mean, some manufacturers claim the coefficient performance when it gets really cold outside does not drop off that much. Other ones show a marked decrease in the increase in the coefficient performance when it gets cold. And some other manufacturers say, I can't even meet the load when it gets really cold. And they're talking about electric resistance heat, which, as you know, that's going to plummet the COP. So you got to be very careful with
we've been doing these projects all over North America, especially in cold climates, and it's never become an issue. So as long as you use the right equipment, and there's equipment out there that's designed to meet the loads, you have to size it right, but it has worked repeatedly.
Yeah, like I said, you got to be careful with the VRF that you pick, because some of them.
Yeah, well, that's part of the specification that's in the whole model. So that is an important element. So one little thing on DOAS ventilation. There's also better ways to deliver it, and this is the ASHRAE 62.1 table 6.2.2.2, zone air distribution effectiveness. And this is a multiplier for what's effective. And so like 0.8 here, effectiveness is ceiling supply of warm air 15 degrees or more above space temperature and ceiling return. What that means is if you push in warm air through a diffuser in the ceiling and it's warmer than what's inside, it's going to cause stratification. So you're going to have that warm air stay at the ceiling, and then it's going to exhaust out of the ceiling, so it's going to stay up there. And so what will happen is you have this separation of the cooler air below and the warm air above. It's not going to mix and dilute. And what you're trying to do is dilute the space. So if the air is within 5 degrees Fahrenheit of what's inside, it tends to dilute and spread into the space very readily. Whereas if it's cooler or warmer, and they're using 15 degrees, I think that's even more than what is really optimum. Tests we did and some research we did at Zender, my former employer in Germany, showed about 5 degrees Fahrenheit. If that differential was 5 degrees or less, the air tended to diffuse and very readily spread into the room. So what this chart shows you is just multipliers on good, better, best to actually deliver that air, that ventilation into the room. What you'll see is this 1.2 is the best option, is floor supply of cool air and ceiling return. What that means is cool air is going to come in at a floor register or low on a wall, and that air will warm up in the room because of people and equipment. If you've got computers, whatever it is, sun coming in, that air warms and then goes toward the ceiling and then goes from low to high and then is taken away with ceiling diffusers. Often it's referred to as displacement ventilation, and it's very effective. And so you have a better, let's call it multiplier here. And so that's another factor with optimizing ventilation and using your ventilation air the most effectively. Michael asked, can I speak further to virus deactivation and ventilation? There are a couple of different options that are being tested and focused on. Ionization is one of them, where you put an ionizer in the ventilation system, so in the duct or in the unit itself. And the ionization, when you ionize the air, you basically are killing viruses. It contributes to killing them off. The other one is UV, and UV light will also kill various pathogens. So they're both being used. One thing that we're concerned about with UV is UV tends to destroy things beyond viruses. So if you put a UV into an HRV, for example, you may destroy plastic, rubber, seals, anything like that. We're very cognizant of people saying, "Hey, I want to put UV in." You can put UV in, but put it down the duct and where that UV light is not going to impact anything that it could actually destroy. And that's an important consideration. Ionization, there are multiple companies working with ionization, ionizers, and we are actually doing some research. I actually just saw some preliminary research out of our lab in Oregon, and we're learning some things about the actual distribution and the ionization, both in the ductwork and in the rooms themselves. And so far it's turning out that it's the level of ionization and effectiveness is directly related to how much ventilation air you're using.
So Barry, that's the thing that, this is Bill speaking from the SCA. That's the thing we're working with the central unit manufacturers. What you just said, like if you put the BPI, bipolar ionization, in the central unit, in the unit itself, the ion charge dissipates as you go down the ducts. So,
right.
And so some people say, well, yeah, we know that and we anticipate that, but we put such a charge in at the central unit, by the time it comes out the terminal diffusers, it's still got enough ions to do its job. So we're looking into that, and as you noticed, as you stated, with the UV down the duct, possibly putting bipolar BPI units further downstream in the ductwork. So, you
Right,
know, there's a less attenuation of ions. But we're all in a learning curve here with this.
right. And we're doing some research. We're working with GPS. They're a pretty well-known company doing that. And
Okay.
so we're doing some testing in our lab with them in conjunction with GPS. So, you know, it's something that's right in the kind of thing we want to deal with. And again, you got to look at the the other unintended consequences. Like I say, UV is a big one, you know, and it's something I was aware of. Fortunately, some people were starting to do that, and I said, "Whoa, whoa, whoa! Don't put it anywhere near our equipment because could destroy things like seals on motors and other things that UV is really harsh on." So you have to be aware of those things. So to wrap up, we've got just about 5 minutes left. So I'd like to just talk a little bit about these projects, and I call this step by step, to just give you some insight, everybody listening in, on what it takes to do these projects, because it's not necessarily easy. This is one of the things with you know, the whole COVID thing. We're working with some schools, doing classrooms in schools. We're doing ventilation there, doing offices and so forth. This is not just going in and putting in an ionizer on a system or changing the filters. This is a whole system. And so it's a little more involved. And so just to give some insight, that Terrytown project, I'm kind of using that as an example. This is my colleague, Aubrey Gaware. This is a distributor in Massachusetts where we're doing a full day workshop. And sitting right here on the right there is the contractor from that Terrytown project who came up to Massachusetts and went through our workshop. And he went back to the owner and said, "Hey, they have this really neat model. I think we should look at it." And that was the beginning. And then from there, we did a study. We got the contractor, the distributor, our rep, people from the heat pump company, and ourselves were involved. Basically put a team together. And then this is RDH Building Science. They're pretty big out of Canada, and they have an office in Boston. And so they did a complete energy analysis because the building owner wants to know how much energy they can save so that they can figure out what the payback is going to be. That's a funny thing. These building owners kind of want to know what the costs are going to be and when they're going to get their money back. And so we did that analysis. We took their utility bills. We took the model and put it into worked up a model for them. This is Fujitsu has a tool that basically it's an energy modeling tool that does VRF and you know, heat pumps and HRVs, ERVs fairly well. And we did the model. Then with that, if there are incentives, in this case, Con Ed had an incentive program. We took that to Con Ed and then applied for incentives for the project. And this is very common. As I mentioned, we're working with NYSERDA to do projects with utilities across the whole state. We are working with ComEd in Chicago. We haven't got that approved, but we've submitted to do pilots with them, and they would incentivize it. This is NYSERDA's list of heat pumps across here, and you can see different utilities: Central Hudson, Con Ed, National Grid, New York Energy and Gas. They'll have a different number here. This is dollars per 10,000 BTUs of heating capacity for the heat pumps. So it's anywhere from $1,000 to $2,000 per, little less than a ton, call it. So we looked at the incentives and we got an incentive for that project. NYSERDA is also doing, as a COVID response thing, through the Green Jobs program, 0% financing on small projects. That's another opportunity. This is Efficiency Maine has incentives for heat pumps. And so we put together the whole project from there. And just to give you an idea what some projects look like. This is a commercial project in Maine where we put the ERVs on the roof, heat pumps. That's what it looks like inside, and we're providing both ventilation, heating, and cooling to a manufacturing facility that has been through COVID, operating with over 100 people in this building. And I'm knocking on wood, have had not a single case with COVID, and everybody is working. And we like to think that we've played a part in that by having optimized ventilation in the space. This is a bank building you can do as a retrofit. So we've got the ventilation here and the heat pumps here. These are electric, very inefficient systems, PTAC systems that are all electric. Those have been deactivated. They're also bringing in outside air from the roof to a couple of furnaces in the basement directly. We're going to save them probably 80% of their energy. And it also is ready to open, as I say, with good ventilation system. Those incentives are out there for all sorts of, all across the country. You can find these on the desireusa.org. And that's down in North Carolina. It's not always all fully up to date, but mostly. So you can access that to find what incentives there are for that would tie in. And then, as I mentioned, putting together the team. So we've got, this is the contractor, and this is a manufacturer's engineer and a rep, and well, here's the rep, and here's the distributor. So they all played a part in developing a budget for the project and working with the owner and the contractor and putting this whole thing together. And then that's what the roofs did look like. All this big equipment's been removed. There's a second bank of these heat pumps down here. And again, there's 4 blue boxes on the roof with ventilation systems. And that project on the inside, they have heat pumps. So they were able to go in after hours, run all the lines, refrigerant lines, and put in the indoor units in the ceiling mostly. They do have some cassettes on the walls with the thermostats. One of the other takeaways here is that because they put more, in effect, terminations with heating, cooling in individual spaces, they were able to improve comfort for people. As you know, some people like the temperature a little different than others, and a rooftop unit that's just blowing air into a large zone has difficulty keeping everybody happy. I kind of call it the Goldilocks effect. A third are happy and a third are cold and a third are hot. One of the reasons we exceeded the model significantly on this project is that I surmised at the beginning, I said, I'll bet that they've got a whole bunch of electric resistance heaters under desks in this office building. And sure enough, we found over 50 of them, 1,500 to 2,000 watt electric heaters under desks. And they were using them both in the winter and in the summer. The rooftop units blowing cold air into the spaces. Some people, again, cold, some people comfortable, and some people warm. And so the people who were cold were actually running space heaters in the summertime. So I think that's a part of why we exceeded the model, is that we got rid of those because the comfort level is improved. So with that, I think I wrapped up just about on time for everybody.
Yeah. I just had a quick question.
Yeah.
Which is, because you said for most of these that the client was in place, the tenant was in place. Did you typically keep the existing ductwork, or?
Yes, we were able to repurpose most of the ductwork. The exhaust, it is a recirculating system, so
Yep.
the return was able to tap into. The one thing we try to do is capture, usually bathrooms are either on a stack or direct exhaust, and we try to capture that. So we tie that stack into the return side. And there's some, individual spaces may have a little bit of work to do a little bit of duct work, but for the most part, they repurposed the existing duct work. So they were able to leverage that. It ends up being oversized because it's not doing heating, cooling, and ventilation. It's just ventilation. But that keeps our static down. You just have to make sure that the ducts are sealed. We recommend AeroSeal if it's needed, to make sure that you're not losing air in the ceiling spaces and so forth. And to make sure that you can get it to the far reaches and make sure it doesn't all get dumped off into the beginning of the ductwork and never
You
make
have
it.
to put, you have to tune.
Yeah,
your
we do some
dampers pretty
dampering. There
well.
was some dampers added and sealing done, but other than that, they were largely able to do it, and it really was, you know, the results have been very positive.
And then the other question is, you showed mostly commercial projects, but I'm assuming that maybe because you haven't had much in the way of multifamily retrofits, which is a whole other beast.
It is, and multifamily is extremely challenging because they had their existing systems, and most of the multifamily we've looked at are bath fans either blowing up a stack or blowing directly out, and fresh air blowing into the hallways.
Yeah.
And it's not ventilation for starters, and
Right.
Nobody should call that ventilation. It's exhausting bathrooms and blowing air in hallways. That's not the same. And so getting ductwork into and out of apartments is a bigger challenge. We've done it, and you can do it, and we've had, you know, success in a couple projects where there was enough of a plenum in the hallways, for example. We put a unit in the ceiling at the end of the hallway per floor, and we can ventilate each space that way. But that's not always the case. And we've seen, I can tell you, I've been on multiple projects where we walked the project and just threw up our hands and said, this is going to be just impossible.
Right.
So multifamily is a different nut. We are working on it. We've actually got some solutions specific to that we're working on as well.
Oh, there we go. Now you're gonna have to do another presentation.
That we are working on a you know, specific, targeted, engineered from the ground up solution for that.
Yeah, that would be interesting, but at this point, it's probably proprietary.
Yep, I'd have to find you and kill you, Caleb.
Do we have any other questions from anybody? Either throw it in the chat or unmute yourself. Well, doesn't seem like it. Thank you again, Barry. Do we have another one of these, or this is the final?
One last one in 2 weeks.
One last. Yep.
2 weeks from today.
2 weeks from today, everybody.
2 weeks today, I'm going to be talking about actual applications. So multifamily, offices, retail, that type of thing. We're going to break down, you know, kind of best practice for ventilating those types of buildings. So that's a pretty good session as well. And we'll talk about different approaches to providing ventilation. Like I say, multifamily and retail offices and so on. Okay, Caleb, we all set?
Obviously knows. Yep, I think we're good. So anybody who wants to tune in 2 weeks, you can find us on the New York Passive House website or Meetup or Eventbrite, and just, you know, look for New York Passive House. And thank you, everybody, for coming.
Thank you, everyone.
Thanks, Barry.
Thank you.
Another good one.
Have a great afternoon.
You too.